Calorimetry, heat. Heat is that form of energy which flows from a hot body to a cold body when they are kept in contact. Units of heat. The SI unit of heat is joule, symbol capital J. The other most commonly used unit of heat is calorie, symbol cal. 1 calorie or 1 cal is equals to 4.186 joule or 4.2 joule nearly. Temperature. Temperature is a quantity which determines the direction of flow of heat on keeping the two bodies at different temperature in contact. The SI unit of temperature is Kelvin. Factors affecting the quantity of heat absorbed to increase the temperature of a body. The mass of the body, Q, is directly proportional to m. The increase in temperature of the body, Q, is directly proportional to delta T. Specific heat capacity of the body, Q, is directly proportional to C. Thus, Q is equals to mc delta T. Thermal or heat capacity. Definition. The heat capacity of a body is the amount of heat energy required to raise its temperature by 1 degree Celsius or 1 Kelvin. Units of heat capacity. The SI unit of heat capacity is joule per Kelvin. Heat capacity is the amount of energy supplied upon rise in temperature. Heat capacity C dash is equals to Q upon delta T. Specific heat capacity. The specific heat capacity of a substance is the amount of heat energy required to raise the temperature of unit mass of that substance through 1 degree Celsius or 1 Kelvin. Specific heat capacity C is equals to Q by m delta T. Units of specific heat capacity. The SI unit of specific heat capacity is joule per kilogram per Kelvin. Relationship between heat capacity and specific heat capacity. Heat capacity C dash is equals to mass into specific heat capacity. Calorimeter. A calorimeter is a cylindrical vesicle which is used to measure the amount of heat gained or lost by a body when it is mixed with another body or substance. It is made up of a thin sheet of copper because copper is a good conductor of heat, so the vessel soon acquires the temperature of its contents, and copper has a low specific heat capacity, so the amount of heat energy taken by the calorimeter itself from the contents to acquire its temperature is very small. The outer and inner surface of vessels are polished so as to reduce the loss of heat due to radiation. For insulation, it is placed inside a wooden jacket. The space between the calorimeter and the jacket is filled with some poor conductor such as wool, cotton, etc. to avoid the heat loss by conduction. It is covered with a wooden lid to avoid the heat loss by convection. Principle of method of mixtures or principle of calorimetry. When a hot body is mixed with a cold body, heat energy passes from the hot body to the cold body till both the bodies attain the same temperature. If no heat energy is lost to the surrounding, that is, if the system is perfectly insulated, then heat energy lost by the hot body is equals to heat energy gained by the cold body. This is called the principle of method of mixtures or principle of calorimetry. The principle is based on the law of conservation of energy. M1C1 delta T is equals to M2C2 delta T2, where M1, M2 are the masses, C1, C2 the specific heat capacity, and T1, T2 are the temperature of the two bodies, and T is the resultant temperature of the two bodies. Natural phenomena and consequences of high specific heat capacity of water. The climate near the seashore is moderate. Hot water bottles are used for fermentation. Water is used as an effective coolant. In cold countries, water is used as heat reservoir for wine and juice bottles to avoid their freezing. Farmers fill their fields with water to protect the crops from frost. All plants and animals have high content of water in their body. Some examples of high and low heat capacity. The base of cooking pan is made thick. The base of an electric press is made thick and heavy. The vessel used for measurement of heat, that is calorimeter, is made up of thin sheet of copper. Change of phase or state. The process of change from one state to another at a constant temperature is called the change of phase. It is brought about by the exchange of heat. Heating curve of ice during melting. From the graph, it is clear that the temperature of ice remains constant, equal to 0 degrees Celsius in the part AB, till the whole ice melts. The constant temperature at which the ice melts is the melting point of ice. The heat supplied during this time is being used in melting the ice. After this, the temperature of water formed by the melted ice begins to rise from 0 degrees Celsius to the part BC. Effect of pressure on the melting point. The melting point of the substances which contract on melting like ice decreases by the increase in pressure. For example, the melting point of ice decreases by 0.0072 degrees Celsius for every 1 atmosphere pressure rise. On the other hand, the melting point of the substances such as wax, lead, etc., which expand on melting, increases by increase in pressure. Effect of impurities on the melting point. The melting point of a substance decreases by the presence of impurities in it. The melting point of ice decreases from 0 degrees Celsius to minus 22 degrees Celsius on mixing salt in it in proper proportion. This fact is utilized in making the freezing mixture by adding salt to ice. The freezing mixture is used in preparing kulfis. Heating curvature for water. From the graph, it is observed that initially at A, water is 20 degrees Celsius room temperature, and then with the absorption of heat energy, the temperature of water rises continuously in the part AB where it is in the liquid phase. At B, the boiling starts and the temperature does not rise further to part BC, although heat energy is being continuously absorbed. The part BC is thus parallel to the time axis and represents the boiling of water. The particular temperature, 100 degrees Celsius, at the point B is the boiling point of water. Effect of pressure and impurities on the boiling point. The boiling point of a liquid increases with increase in pressure and decreases with decrease in pressure. For example, a pressure cooker can be used for cooking at high altitudes such as hills and mountains where the atmospheric pressure is low. Thus, cooking at high altitudes, if done in open, becomes difficult and takes much more longer time. The boiling point of a liquid increases by addition of impurities to it. If common salt is added to water, it boils at a temperature higher than 100 degrees Celsius. Hence, we add salt while cooking pulses. The water then provides sufficient heat energy to its contents before boiling, and now it is at a higher temperature, so the cooking becomes easy and faster. Latent heat and specific latent heat. Latent heat, when expressed per unit mass substance, is called specific latent heat. Definition. Specific latent heat of a phase is the quantity of heat energy absorbed or liberated by the unit mass of the substance for the change in its phase at constant temperature. L is equals to Q upon M. Unit of specific latent heat. The SI unit of specific latent heat is joule per kg. Natural consequences of high specific latent heat of fusion of ice. Snow on mountains does not melt all at once. In cold countries, water in lakes and ponds does not freeze all at once. Drinks get cooled more quickly by adding pieces of ice than ice cold water at 0 degrees Celsius. When ice in a frozen lake starts melting, its surrounding becomes very cold. It is generally more cold after a hailstorm when ice melts than during or before hailstorm. Example: a slab of ice is 0 degrees Celsius is constantly heated till the steam is formed at 100 degrees Celsius. Draw a graph showing the change in temperature with time. Label the various parts of the graph properly. The graph shown the change of temperature with time is given in the figure above. A piece of ice is heated at constant rate. The variation in temperature with time of heating is shown in graph. What is represented by part AB? What does the part CD represent, and what conclusion do you draw during the nature of ice from the graph? First, the part AB represents melting of ice at 0 degrees Celsius. Second, the part CD represents the boiling of water at 100 degrees Celsius. Third, the ice initially is in solid state at minus 10 degrees Celsius. On heating, its temperature rises to 0 degrees Celsius. It then takes some heat at 0 degrees Celsius to melt in water at 0 degrees Celsius, which is called its latent heat. A substance initially in solid state is 0 degrees Celsius is heated. The graph showing the variation in temperature with the amount of heat supplied is shown. If the specific heat capacity of solid substance is 500 joule per kg per degree Celsius, use graph to find first the mass of the substance, second the specific latent heat of fusion of the substance in the liquid state. First, in the graph, part AB represents the increase in temperature of solid substance from 0 degrees Celsius to 80 degrees Celsius on absorbing the heat Q equals to 800 joule. If m kg is the mass of solid substance, then heat absorbed Q is equals to mass into specific heat capacity into rise in temperature, or 800 is equals to m into 500 into 800 minus 0. Thus, m here is 0.02 kg or 20 gram. Second, in the graph, part BC represents the change of state of substances from solid to liquid at 80 degrees Celsius on absorbing the heat Q equals to 1600 joule minus 800 joule, that is 800 joule. If L joule per kg is the latent heat of fusion of the substance in the liquid state, then heat absorbed Q is equals to mass into latent heat of fusion, or 800 equals to 0.02 into L. Thus, L here is 40,000 joule per kg.